Hi everyone, thank you for being here. I'm Nora,
I'm Becca.
And I'm Emma.
and today we're going to be talking about plasmonics and an experiment that we did during the week. So plasmonics is a study of plasmons, which is the excitation of electrons in response to light, and we'll elaborate more on it later in the presentation. If you guys don't know what that means, it's okay. So plasmonics has really been an important part in our lives even before we knew it. So a perfect example of this is the Lycurgus Cup, which is from the Roman era and it was made by the Romans. So basically it's just a cup that if you shine light on one side of the cup and you look at it from one side, then it looks red, and if you stand on the same side as the light, it looks brown. So this has to do with absorption and scattering, which is a big part of plasmonics, and we'll also elaborate on that later too, but it's basically how the lights excite the electrons and stuff and the colors that they emit. Another example of why it's really important and it's a big part of our lives is because of the Notre Dame Cathedral, as we all know, recently burned down, but luckily one part of it, which was the rose window, didn't burn down, and that's a big part of plasmonics and how it was made. So the stained glass windows are well, we know they're colored, and so it has nanoparticles in them, and it's also kind of due to absorption and scattering, and again, we'll elaborate on that later. So despite the fact that the Romans didn't know anything about science and nanoparticles and plasmonics specifically, that it was still a big part of our lives, so that's why it's also important in later times, because even though you guys might not know it, plasmonics and everything is a big part of all aspects of our lives. So now we're just going to start by looking at the analogy.
Okay, so I'm going to be talking about the top half of the picture. So the first thing you want to notice in the top half of the picture is that the citrus flower is missing for the second beaker, and this is significant for a few reasons. So I'm going to be talking about the underlying topics that we learned. We learned that you need 3 things to create stable gold nanoparticles, and this includes Au gold with a charge of 0, a reducing agent, and a capping ligand to prevent the nanoparticles from agglomerating and clumping together. And I know that that's a lot of terminology, but I'll explain. So without the capping ligand, the particles would be unstable and inefficient, and we wouldn't be able to make stable nanoparticles like we did. In the experiment we did, we used AuCl3, which is gold chloride, and citrate, which acted as both the reducing agent and the capping ligand. So the reducing agent, gold, Au has a charge of 3+, so we wanted to make that 0 in order to make stable nanoparticles. So here we see in the picture that the first beaker has citrus flower. Because it has citrus flower, the nanoparticles were not able to agglomerate and clump together, which means that we were able to make stable nanoparticles, which is why beaker 1 has a finished cake that looks good. And the second one doesn't have citrus flower, therefore they had no citrate. There was no, it could not prevent agglomeration, which is why the cake looks like a big mess. And now Becca's going to talk about the second half.
Yes. So the second half represents plasmon resonance, which is basically when a sea of electrons on a particle interact with light and they give off color. So as you can see in the first part, there's clear directions that says more milk, whip slower. So basically, the thing about plasmon resonance is that they both have to be on the same wavelength and have the same frequency to produce color. So in the picture, on the left side, the person is following the instructions, and with the lesser milk, they're stirring slower, or more milk, they're whipping slower, and with less milk, they're whipping faster. But the person on the right isn't following the instructions. So the person on the right doesn't, the product isn't right, which is the same thing with plasmon resonance, where the color wouldn't come out. But the person on the left, they're following the instructions right, which produces the color or the product. And one is still and one is thick, because depending on the wavelength and depending on the frequency, it gives off the certain color.
Okay, so next we're going to be talking about surface area to volume ratio, which we learned was really important in nanoscience. So in the experiment we did, we made both nanospheres and nanostars. A nanostar, because it has the legs of a star, has a higher surface area to volume ratio, whereas a nanosphere, because it does not have the legs of a star, has a lower surface area to volume ratio. And the important takeaway we learned from this is that nanoparticles with a higher surface area to volume ratio are less stable because it allows for more defects. The opposite is true as well. Nanoparticles with a lower surface area to volume ratio are more stable. And now Becca's going to talk about plasmon resonance.
Or absorption and scattering.
Yeah.
Yeah. So back to what Nora said about the Lycurgus Cup. So as she said, you see two different colors, and that's depending on what side you see from light. So one side is absorption, and this means that the light is giving off the complementary color when it's hitting. So that's where you see the one color. And then on the other side, you see scattering, which is when the light given off returns the light, so the light's bouncing back instead of being absorbed, and that's the difference between absorption and scattering. And then that's the Lycurgus Cup. So that's, as Nora said, that was the very beginning of nanoparticles, and then now in the future we're coming up with new ideas, and that's where we have something called the photothermal effect, and this is when nanoparticles heat up due to light being shined on them. And this is used to target tumor cells in the body by, the nanoparticles are directly targeted at the tumor cells, and then this activates the first line of defense in the immune system, which is a lot less invasive than chemotherapy or and risky than chemotherapy. So we're developing new things. So even from the Lycurgus Cup, which was so long ago, and then also now photothermal effect, which is we're developing right now, nanoparticles and plasmonics is being used throughout time.
Okay, so the last final thing we learned, or the biggest takeaway from this experiment, was that plasmon resonance and the colors they emit depends on size and shape. Size and shape is really important. Changing either the size or the shape or both can create new localized plasmon resonances that would change the colors absorbed and thus the colors reflected. And so these are the 5 main topics that we learned on plasmon resonance. Thank you.
Okay, questions?
No.
All right.
Hi there. Great job, guys.
Thanks.
Very interesting. So you referred to some back in history nanoscience, both the color in the glass for the rose window and the Lycurgus Cup. And you mentioned that that was a first use of nano. What are the nanoparticles or nanostructures that go into that glass? Were they doing something special without noticing it, or is it inherent in every object?
Basically, they were doing something without noticing it because what gives off, like in the stained glass window, it's gold or silver nanoparticles, which is in it, but this gives off a different color. So technically, they're using the metal and the color comes off, but they didn't know that was the connection to it.
Yeah, so they must have been doing something without realizing what they were doing,
Yeah.
because obviously they didn't have the knowledge that we have today about nanoscience. But throughout during the process of making the glass structures, they were able to like create nanoparticles, which is why we have that like rose color effect that we see in the rose window in Notre Dame.
Other questions? So just one comment. Okay, just one comment for you guys. Yeah, what they did is they just dumped gold or silver into their vat of melting glass and said, "Oh, the color changed." They didn't say, "Oh, I'm making gold nanoparticles,"
Yeah.
but actually they were making gold nanoparticles. The gold they dumped in there aggregated into little nanoparticles. So that's exactly the question. Oh, you have your own mic.
Okay, so my question is about the top half. So you mentioned that the citrate has 2 purposes, right? So which purpose do you think it's serving here? You said?
Oh, okay. So in our experiment, citrate acted as both the capping ligand and the reducing agent. But thank you for pointing that out, because we wanted to talk about. So the artist of this drawing included milk and citrus flower, and here citrus flower acts as the capping ligand, because milk we see is negative, or she talks about. If you can see the label, I'm
It
not sure if
says
you can.
underneath, it says our milk is so cold it's negative, which also reacts with the gold that we use, because gold is a positive charge, and since the milk is a negative charge, would reduce the gold to a neutral charge.
Yeah.
AU0, which is what we needed to make those stable gold nanoparticles.
It could be the capping agent. It could also, I think, be the reducing agent based off of the results, I would think. Maybe. Right? Because in one case, you have something that does look like it's one agglomerated piece, right? The cake. And then in the other case, it sort of looks like a disjointed mess. So it could be, I think, possibly the reducing agent. But you mentioned that the citrate does both of those functions.
Yes.
Yeah.
So it could be either. I guess we'll
Yeah.
find out when we ask the artist.
So then my question is, what are the limitations of this? Well, I didn't want to tell people not to talk about that. I just want you to use good language when you do so. This captures some aspects of this experiment, but surely baking a cake does not directly or completely map onto making gold nanoparticles. So what are aspects of the experiment that are not captured in this?
Well, I think the shape and size she couldn't really incorporate into the thing, because it would be hard to kind of incorporate it into this analogy, but shape and size also do play a really important factor.
I do actually think that the shape is a part of it. If you look at the two whipped creams,
Oh, yeah.
I think
Yeah,
they
I
do.
guess so.
So how would those track? So which one is representing which, do you think?
For shape and size?
Or at least for shape.
Wait, sorry, could you repeat the question?
Yeah.
So if you look at for the successful baker, they've got two different whipped creams, right?
Yeah.
They look like they're different shapes. So how does that relate then to the different shapes of the gold?
Oh, so like we talked about in the presentation, we learned that size and shape have a effect on like the kind of like color that is emitted, which is why we see that like when she uses like the different sizes or shapes of the whipped cream, they created different products, which was one of the points that we learned in the experiment.
I think just to quickly clarify, I think one of them has star-like peaks to it, like spiky, it's like a spiked stiff peaks, and the other one's got like more globular spherical shapes. So I think that was another intention of the artist as well.
I think my eyes are too old to see the difference between the stars and the globes. Okay, one more question. Oh, audience.
Oh,
Yes,
okay.
awesome.
So you mentioned briefly the medical aspect, like with cancer.
Yes.
And I know that the rest of the presentation, I made us to miss something, because you know a lot more than I do about this. Talked about gold and almost about a visual image. How is this part of the medical part? Is it the light that it shines in a certain item? Is it how you can read it? Or did you just mean that's nanoscience in general?
Well, it relates. So in our experiment, we were making nanoparticles, and so those nanoparticles will be implemented into the body systems, and that's how it relates to biomedical. So like the things we were making in labs and stuff, they have the ability to the photothermal effect. We didn't explore that area in our experiment, but that is another aspect that nanoparticles have.
Okay, but let me just ask a clarifying thing. So you talked about the fact that you made different kinds of nanoparticles and that they could absorb different colors of light based on their size or their shape. And that's the essence of this experiment. What is the photothermal effect? So after you absorb the light in the photothermal effect, what do you do with that light energy?
Well,
I don't know if we can answer that question very well, but like we'll try. So
Yeah.
what we learned about the photothermal effect is that when nanoparticles have light shined on them, they're like open to like a wider range of capabilities and like applications.
Yes.
So one of the applications like we
Is
talked about
heating.
is the being able to specifically target tumor cells in the body.
But would just go back to like the name, photothermal.
Photothermal.
I think it's taking the light
So it's
and
taking
it's
the light
releasing
energy,
heat,
yeah,
and
and
so
turning it-
as it releases heat, then it kind of kills the cell.
Yeah, that's all it is.
Oh, okay.
It just absorbs light, and metal nanoparticles really efficiently turn that light energy into heat energy.
Yeah.
So they can locally cook things wherever they are when they absorb light. That's
Yeah.
all there is to it. This is our whole point. This nanoscience is not big voodoo. It's simple, but it's cool.
Yeah.
It's always simple. Okay, that was an awesome presentation. Thank you guys very much.
Thank you.